Alright class, today we're going to be going over some examples from the Piecewise Functions Delta Math assignment. So the very first skill is to evaluate piecewise functions graphically. So when you are evaluating a function graphically, you are going to be provided with a graph, and you'll be given a problem where it says find f of blank. So in this case, we're finding f of 1. So recall that this is in function notation. So f of 1 implies that when x is equal to 1, what is the y value? So you look at your graph. On your x-axis, here is 1. So you scroll down to where the graph is. It looks here at 1. When x is equal to 1, f of 1, aka the y value, is -3. Submit it. And there's your answer. If, for instance, you were given a problem where it was f of 2, at 2 there is an open circle. So therefore at f of 2 it is undefined. So let's go back. The next skill that you need to know how to do is how to evaluate piecewise functions. So let's click on this. So you're given a problem. F of x is equal to parentheses x minus 8 squared minus 6 for when x does not equal to 5, and 2 when x is equal to 5. So this is giving you a pathway. This is saying what is f of 5. You look at where 5 is within your piecewise functions. Well, this is saying when x is not equal to 5. So we don't want that. So when x is equal to 5, we plug it into this equation. Well, there is no x value here, so the answer is simply just 2. And you submit it. All right? And you go through the loop. These problems are very, very similar. The third skill that you need to know how to do is how to graph piecewise functions, level 1. So you'll click on that. So here in this example, we need to graph the following function on the axis provided below. You need to click and drag to draw a line. So for instance, that's how you do it. Click the line to delete it. Oops, sorry. And click on an endpoint to change it. So let me try. If I click on an endpoint, I change it from a closed circle to an open circle. And likewise, if I click on an open circle, it changes to, either to an arrow or a closed circle again. So you can alternate between open, close, and arrow, which is really, really cool. All right, so here in this example, we need to graph the first equation. The first piece of our piecewise function is x minus 4 for when x is between -1 and 2. So I highly suggest that you draw a t-table so you have a list of points that you can use. So let me just minimize my screen here, minimize my Delta Math. So for the first piece, we have f of x is x minus 4. So the endpoints will be at when x is -1 and when x is at 2. So because there is no equal sign, it's going to be an open endpoint. So if I plug in -1 and 2 inside this equation, I get -1 minus 4, which is -5. Likewise, if I plug in 2 minus 4 is -2. So when I plug in -1 into x minus 4, right, we get -5. So -1 comma -5 is an endpoint. So let's plot that on our graph. So -1, -5. So it's right there. So keep that in mind. And we're going to drag it to 2 comma -2. 2 comma -2 is right here. So we have -1, -5 to 2 comma -2. Because there's no equal sign, click on the endpoints, to create an open circle. So that is our line. We can double check because this is a linear function of the form mx plus b. Our slope is 1, so that looks correct because it's going up 1 over 1, and the y-intercept is at -4. So far it looks good. Once we're done with that, we move on to our second piece of our piecewise function. Let me do it in a different color. F of x is equal to -x plus 4. This is also a linear function. So now the endpoints are at 2 and 5. So you want to plug in x is equal to 2. When x is equal to 5, when you plug in 2, you get -2 plus 4. -2 plus 4 is 2. And when you plug in 5, you get -5 plus 4, which is -1. So you have a point at 2, 2. So 2, 2 is here. I'm going to click and drag to 5, -1. If you mess up, I believe you can just click on the line to delete it and try it again. I believe, unfortunately, you can't drag the line, which is unfortunate. Let's double check. This is an open point because it's undefined there. So we need to click on the points to make it open. Let's just make sure this is correct. It has a y-intercept. So if I were to keep on drawing this line, it will intersect at 4. The slope is correct. It's at -1. So let's go back to our Delta Math assignment and submit this. It is correct. So that's how you graph these level 1 functions. All of the level 1s should be linear functions. So they should have a slope. They should have a y-intercept, unless, of course, you restrict the domain. So just be careful of the restricted domain and make sure that you click on a dot to indicate whether it's closed, if there's an equal sign, or if it's open, if there's no equal sign. Let's go back, and now we're going to graph some nonlinear functions. All right, so we have a bunch of linear functions here. Step 1, select the function and move with the blue dot if necessary. So the first example, right, this is very similar to what we did in level 1. This is actually a linear function, whereas this guy is not a linear function because it's not of the form mx plus b. So keep that in mind. So this is a line, so this is not bad. So we need to click the line, then we need to move the blue dot if necessary. Since this is a line, we can kind of do it right now. It has a y-intercept of -5, has a slope of -1. Oh, so this is a horizontal line. So how do I delete this? I guess we have to start over. So unfortunately, you can't drag this line. We know that this has a slope of a -1, so we probably should choose this guy. All right, and we need to drag it so the y-intercept is at -5. So there we go. And can we pick another function? Oh, so we can only do one function at a time. So let's move this down to -5. All right, let's start with the piecewise function. Done. Now drag the double blue arrows inward if necessary to set the domain of the function. Okay, so that's cool. So this is very interactive. Our domain is from -4 to -1, so we can drag this piece to -4. So we don't even need to do a table value for this assignment. We still could. We can plug in -4 in here, which would get us 4 minus 5, which is -1. But we can simply just drag this. Nice. So from -4 to -1 is our restricted domain for this linear function. Remember, there's no equal sign, so I believe we just double click. Bam, look at that. We have our linear function. Now this is a square root function, so we're just going to use some transformations. The parent function is the square root of x, which looks like this. And now we're going to use the transformation to shift it down. So it's moving down by -5. So press done, and we just drag it down. Wait, how do we drag it down? Oh no, do I need to start over? It didn't let me, oh no. Bummer, so let's do that again. Oh, that's unfortunate. So here we have this line, press done, then we drag it. So you need to, so what we need to do is we can't transform it later. We need to transform it before we get to the second step. So lesson learned. So press done. Do that. All right, so now this is a square root function. You need to drag it first, sorry. There we go. You need to drag it down to -5. Oh, we can also move left and right. Cool. So move it down 5 units. That's our transformation. It's greater than or equal to 0. So done. Yeah, if it's greater than or equal to 0, we don't even need to move this right piece. We do need to move this left piece. So let's see how that interacts. Finish. So that looks good. Let's double check. This is a line with a slope of -1. The y-intercept would have been at -5. That looks good. It's being restricted from -4 to -1. That looks good. And this is a square root function that got shifted down by 5. It's being restricted from 0 to infinity. So there's a closed circle. That looks good. Submit our answer. And we are done. So that's how you do these type of examples. So just make sure for step 1, you graph the entire function, move it left, right, depending on the function. Then set the domain, left, right, up or down, sorry. Then restrict the domain so that it's between this value and this value. And then click on the point to make sure it's either open or closed, depending if it's equal to or not equal to. All right, so that is all.